So a couple things to note and focus on. So a couple of big major regulatory steps that we're going to focus and spend some attention on. So when your fructose 6-phosphate turns into fructose 1,6-bisphosphate, and then the very last step, when we turn phosphoenol provate into provate. Two big regulatory steps. So notice one consumes ATP, one produces ATP. We'll see one other minor regulation step. And the other minor regulation step is the other one that actually uses up ATP. Where's that? So yeah, way back up at the top at the beginning, hexokinase. But that won't be such an important thing. So if you look at your glycolysis reactions for a minute and just take a big fat overview. So what's the difference between delta G naught prime and just plain old delta G? Yeah, one's biochemical conditions. What are those biochemical conditions? pH of 7, 37 degrees Celsius, and all reactant and product concentrations are present at 1 molar concentrations. How many things do you suppose in your cell are present at a 1 molar concentration? So I'm sure there's something out there that maybe is, but maybe not. That's pretty high concentration. And so if you notice, there's some significant differences between delta G naught prime and plain old delta G. So if you look, like this one here, 23.9 kilojoules for delta G naught prime. How spontaneous is that under biochemical standard conditions? Not very, but look at this. So just slightly negative. And if you look, when your delta G values, the values actually reflected inside the cell, are close to 0, what does that mean? It's near equilibrium, and it's a reversible reaction typically. It could go either way. Change, the reactant concentration, the product concentration, you can probably shift it back and forth any way you want to. But they're reversible reactions. So, however, not all of these reactions are close to 0. Which ones are not close to 0?
How close to 0 does it have to be? Just been like 3 or 4?
So give or take 2 or 3 kilojoules-ish. It's not an exact number I can give you a cutoff, but it's somewhere in there. If you notice, there's a few numbers that'll definitely be outliers here. So which numbers are, reflect reactions that are not reversible under biochemical or under the biochemical actual cellular conditions? First one, sweet, and that's a good place to do some regulation. It's not the best place, we'll find out, but it would be a good place. Where else? So the last one, so turning phosphoenol provate into provate. Where else? So the third one, turning fructose 6-phosphate into fructose 1,6-bisphosphate. Cool. It's no coincidence that those steps are also often the ones we regulate. Not always, but it's very often the ones that are irreversible, that have very negative delta Gs, those are the ones we regulate.
Remind me again, the delta G naught prime is the one of physiological pH?
So, no, the delta G naught prime is the one that's biochemical standard conditions, so which is pH 7, so and stuff like that. But this is the second column is just plain old cellular conditions.
Okay.
This is how it exactly would be in a typical, say, red blood cell. In fact, I think these numbers actually came from a red blood cell. So notice these are the numbers on the right that are really more relevant in this case. So notice it's the delta G naught prime, the biochemical standard conditions, that we talk about reactions being endogonic and exergonic. So in this case, so you might see a question that talks about, endogonic reactions. It's really not spontaneous under standard conditions, which is what endogonic means. How can we still potentially have that reaction happening in the cell? Concentrations, what kind of concentrations might I look for that shift that equilibrium towards products? So I could have high concentrations of reactants or relatively low concentrations of products. Either one of those could potentially make an endergonic reaction actually feasible inside a cell. So there are other reactions that are not feasible, like turning glucose into glucose 6-phosphate, just that all by itself with nothing else. Not a very favorable reaction. How do we make it favorable? Couple it to ATP hydrolysis. So you may get some questions. It simply have you doing some very rudimentary calculations. So if you look at ATP hydrolysis, and if you look at, say, if I had plain old glucose to glucose 6-phosphate up here. So where does that number negative 16.7 actually come from? So, well, in this case, if we take glucose and turn it into glucose, and I'm not going to balance these, by the way, 6-phosphate. So, and if I take ATP and turn it into ADP, so in this case, what's your free energy change for ATP into ADP, according to the chart? Way at the bottom. Negative 30.5. Now, once you combine these two reactions, what's your delta G naught prime? Negative 16.7. What must this reaction have had a delta G value of? I'm asking you to do math in your head. Anybody got a calculator handy? What is it? Let's see. If this was 30.7, it'd be exactly good. Cool. Definitely not favorable, at least not under biochemical standard conditions. So, but in this case, combine the two, and I get a reaction that maybe now is favorable. Now, a couple things you might want to look at in this context. So one is I gave you these two on the chart, right? So I gave you the total and for ATP hydrolysis. Maybe on the test, maybe he just gives you these two. In fact, maybe he gives them both to you a slightly different way. We often give them to you in terms of phosphate hydrolysis. Maybe I give you glucose, 6-phosphate, turning into glucose, and they probably show the inorganic phosphate. And then I show ATP turning into ADP. This would be your negative 30.5. This guy would be negative 13.8. So, and then I may ask you to couple them. So into the reaction we actually know, glucose with ATP giving glucose 6-phosphate. And ask you, what's the delta G? And I might ask you to realize, oh, I got to flip this one around backwards. And if I flip this one around backwards, what happens to that? It becomes positive, and then you have to add them together. So it's not the hardest thing in the world, but if you haven't seen it since Gen Chem, which is a good chance of that, so it might just be enough to throw you. And it's easy points once you realize what you got to do. So if the half reaction you need is backwards, so when I say half reaction, it's probably not the proper term. In this case, it's not redox. So then flip it around and change the sign before you combine them. Sweet. Questions? So going back, your irreversible reactions are often the ones that are highly, highly regulated. Everything that you've studied throughout this context that's been regulated, you need to know it, and you need to know it well. Now here's the deal. Memorizing things, good times. So I need you to repeat after me. Chad is a big dumb idiot. Sweet, I think you can do better than that, but I'll let it slide because I don't really want to hear it. So now, repeat after me again. Chad est un bête stupide idiot. So somebody got it. He probably has a little French in his background. So Chad est un bête stupide idiot means Chad is, instead of a big dumb idiot, really means like a dumb stupid idiot. So, but if you don't know French, if that makes no sense to you whatsoever, it's harder to memorize. So here's the deal. You've got a lot of memorization to do. But if it makes sense, it's easier to memorize. So your goal is not to just memorize everything. And you can do that. So, but if you can make it make sense before you actually memorize it, it'll make your job so much easier in memorizing it. So as far as structures, if that's what he told you, I will defer to that and say, great. So if you were in a 400 level class, we'd probably make you know all the structures as well for everything. But you guys aren't. And so all of the structures is pretty crazy. But if you spend a lot of time focusing on something like you did on the regulatory steps, you probably want to know everything you can about those regulatory steps, maybe including structures. So if he was nice enough to tell you that, then awesome. So enzyme names, I would definitely, especially in these major regulatory steps, also know the enzymes names, know who the reactant is, who the product is, maybe what they look like, so, and how all the regulation happens. So in this case, let's first look at hexokinase. We're not going to spend too much time on him because he is not the most important thing in the world. So I'm not going to draw out any of the structures here, by the way, guys, because I already have. So keep those in mind. Because I'm not drawing them out doesn't mean they're not important. They really are. So we're just going to kind of keep this simple. What reaction does hexokinase catalyze? Good. Glucose to glucose 6-phosphate. This is what hexokinase does. Cool. Cells are smart. Energy is not cheap, and being wasteful with your energy is not favorable to the cell. And so cells are smart. And so the way they regulate things is for a purpose. So in this case, a couple common patterns we see. They're not always all present, but a couple common patterns we see is we see that oftentimes a reactant turns an enzyme on. Not always true, but often true. We also see that if I've been doing this for a while and I got plenty of product, then maybe it'd be a good time if we shut this off, if you will. And so we often see product inhibition as well, inhibiting an enzyme. Those are two very, very, very common patterns. They're not always present, but there's something to look for and there's something that makes sense. So in this case, when we see activated by, there's nothing there. But we do see an inhibition, and who's inhibiting our hexokinase? Glucose 6-phosphate, product inhibition. If I already got a boatload of glucose 6-phosphate, then let's stop making it. I don't need any more. Let the rest of glycolysis catch up, because I may not need that much energy in the immediate time. Cool. And so that's product inhibition. It makes sense. It's something we might expect. Now notice I said, we often see reactants activate things. It's not the case here. It happens often. We'll see it later on today and stuff like that, but it doesn't happen here. So just keep in mind when you're memorizing these, just because something makes sense doesn't mean it happens either as well. So one other thing we'll look at. So what do you suppose might be accumulating in a cell that's really needing some energy badly, really needs to do some glycolysis? ADP or AMP. Both ADP and AMP are evidences that you don't have a lot of energy. So you're at kind of a low energy situation in the cell. What would be a high energy situation? ATP. So, but notice, if I had some ATP and it's no longer ATP, what's it going to look like? In all likelihood. Well, either ADP or AMP. It got hydrolyzed in one way, shape, or form. You've got a pool of adenosine, monodi, and triphosphate. And it's, until you get some more in dietarily or something like that, it's just being shuttled between one form or another. And so instead of talking about high amounts of AMP or ADP or low amounts of ATP and vice versa and stuff like that, we usually just look at ratios. And so we might usually look at a ratio of ATP to ADP, or maybe ATP to AMP, things like this. We often just look at it as a ratio instead, but it means the same thing. So if this ratio is high versus low, just means high energy situation if you got lots of ATP relative to ADP. So, however, if this ratio is low, then it means you're in a low energy situation because you have lots of ADP and not so much ATP. So when would it be a good idea to turn glycolysis on? When you're in a low energy situation. When would it be a good idea to turn it off? When you're in a high energy situation. Keeping that in mind as well when you're looking at these regulatory steps, because those also make sense. So in this case, now we'll look at the two major regulation points. So first is PFK1. So what's the major reaction for PFK1? So fructose 6-phosphate to fructose 1,6-bisphosphate. So let's look at what activates PFK1. AMP activates it allosterically here. Does that make sense? Why does that make sense? Evidence of low energy, so let's get glycolysis going. Okay. So what else activates PFK1? Fructose 6-phosphate. Does that make sense? Yeah, that's the reactant for the reaction turning it on. Again, something that makes sense. And I got lots of that building up. Well, let's use it. So fructose 2,6-bisphosphate. Does that make sense? Nope, unfortunately, it doesn't make sense for anything we talked about. That's one you need to memorize. So, insulin. Insulin. Where's insulin? Is it in your cell, necessarily? Where's the insulin? Bloodstream. What's it for? Yeah, it's getting, when you've got a lot of sugar, because you just ate, so then you get insulin released so that you can do something with that sugar, which either can lead to storage or glycolysis, depending on what's going on in the situation. So in this case, if you just ate and there's lots of sugar in your bloodstream, that's when insulin gets released. Would it make sense that that would want to turn on glycolysis? Yeah, if you've got lots of glucose available, then by all means, let's get using it. Let's make some energy. So let's look at the inhibitions. ATP inhibits PFK1. Does that make sense? Because ATP is energy of what? I got lots of energy. Maybe it means the cell's at rest. Has tons of energy and I'm good. So I've stored up enough, as much as I can. Don't make any more. I'm good. And so great. Then let's shut down PFK1. So fructose 1,6-bisphosphate. Does that make sense? Why does that make sense? Product inhibition. Great. If I already have produced a lot of this, then let's stop producing it. Let's let the rest of glycolysis catch up. Citrate. We haven't talked about it yet. Where's citrate? So citrate is way down the chain at the beginning of the citric acid cycle, right? So in this case, we talked about product inhibition. It doesn't necessarily have to be the immediate product. Maybe it's even something further down the chain. That's also evidence that I'm in a high energy state, if you will. I don't really need to keep making not just more of this, but more of anything all along the chain that it leads to. And so citrate shutting it down actually kind of does make sense. So we might expect something before this point to turn it on, and anything after to turn it off. It makes most sense when it's the immediate thing after, but it doesn't just have to be that first thing. It could be something down the chain. So that does make sense. So, and finally, glucagon. So and glucagon and insulin are usually fairly antagonistic and do pretty much the opposite. So another hormone in your bloodstream. Cool. You need to know all of these. Make flashcards, do what you need to do, but you need to know all of these. So pyruvate kinase, what reactions does catalyze again? Good, turns phosphoenol pyruvate into pyruvate. Cool, let's look at its activators. Who activates this? AMP, does that make sense? Yeah, AMP low energy, then yeah, let's keep glycolysis moving. Okay, so fructose 1,6-bisphosphate also activates it. Does that make sense? How does that make sense? It does. Good, so here, fructose 1,6-bisphosphate is way back here. It doesn't have to be the immediate reactant that turns it on, but anything beforehand turning it on makes sense. If I've got some of the reactants leading up to this point pooling up, let's use them up. So in this case, let's see what shuts it down. Inhibited by ATP. Does that make sense? Yeah, again, if we have lots and lots of energy, lots of ATP, then we don't need to do any of this catabolic stuff anymore. Shut it all down. So acetyl-CoA shuts it down. Does that make sense?
Yes.
Yeah. So notice acetyl-CoA is next thing down here on the food chain after pyruvate. So it's not the immediate product that's shutting it down, but the very next one after. So a form of product inhibition, but not just the, in this case, not the immediate product. Cool. Who else shuts down pyruvate? Or at least, how else can we shut down pyruvate kinase? Phosphorylation. What does that mean? This is covalent modification. We're going to phosphorylate some alcohol residues on this enzyme, on this pyruvate kinase, serines, threonines, things of that sort, maybe tyrosines. So we phosphorylate them. That puts a negative charge on that particular residue, or, you know, and I might do it in a few locations even. And that puts some negative charges there. What might that result in? Might cause the enzyme to change its conformation. And if it changes its conformation, it could either activate it or inactivate it. In this case, what does phosphorylation accomplish? It inactivates it. So keep in mind, every time phosphorylation, this is covalent now, we're forming covalent bonds on these serine, threonine, and tyrosine residues. Keep that in mind. Everything else we've been talking about up till now, as far as some of the substrates, have been allosteric. So that's phosphorylation of pyruvate kinase enzyme. So phosphorylating the enzyme itself. Cool. So last but not least, alanine. So alanine. We can make alanine make sense if we introduce some other stuff, but we're not going to go there. So just memorize that one. One other thing. I didn't point this out, but you definitely need to know this. So your major regulatory steps, you see that first one? And I really wanted to point this out and didn't. This is your commitment step in glycolysis. What do I mean by commitment step? So yeah, once you get here, you're not going back up. So if you're at fructose 6-phosphate, you could use that for some other stuff, potentially. But once you turn it into fructose 1,6-bisphosphate, it is now earmarked to carry out incomplete glycolysis.